Good evening, everyone. Welcome to lesson 3 of Unit 2 and a little bit of an introduction into polynomials. All right, so in this lesson, we're going to do some of the basics of the definitions of polynomials. In the past, in algebra, you have dealt with two types of polynomials, linear and quadratic. Quadratic being the ones that form the parabolas. And they have even linears and quadratics, even though they have a lot that's different, they do have quite a bit that's the same too, and that can be generalized for all sorts of different graphs. Linears have an x term, so functions like 2x plus 3 is linear. Um, Functions such as x squared plus 2x plus 3, that's a quadratic. But then if the exponent gets higher than that, x to the third, x to the fourth, they have some differences, but some similarities. And that's what this lesson is going to learn about the definitions about that. Okay, so which one doesn't belong? Okay, a little bit of a warm up here. I'm going to give you four little expressions, and let's look at some of the similarities and differences between them. Okay, so first off, is there anything that you noticed, like why something might be different? Okay. Probably the most glaring notice when you look at these, there's x squared, there's x to the third, there's x to the fourth. So B might be different because it's got an x to the fourth, right? So an x to the fourth term. But then there's other things like C has this 1/3 term. Okay? We wonder what that might do. Um, and then there's some other interesting things that happen here, like 4 to 2D has no constant term. So they each have their own little differences, right? Okay, so as usual, you can kind of make a case for each one of these um, as to what's going on. Now, what makes A different from all the others? Now, in particular, one of the things that you look at is B, C, and D. When you look at the powers of X go from the highest to the lowest. So 4, 2, 1, no X. 2, 1, 1/3, no X. So these terms are not in decreasing order. Well, actually, technically, this one isn't either. So D really isn't either. Um, but it has some like terms as well. An x squared and a 2.4x squared, which we could possibly combine here. Okay. Um, so A has and D kind of have a similar kind of odd difference, and we wonder what that might do to our function. Okay. All right, so let's start with some quick definitions, shall we? The most important ones for us right now is degree. So the degree of a polynomial is the highest exponent occurring on x when you write the polynomial out as a sum of non-zero constants times powers of x with like terms collected. Okay, that just means that we have very few like terms. Uh, the expression is in simplest form as possible. So when I go back to these expressions here, like I look at A, right? Um, for A, this expression cannot be simplified anymore. 4x squared, x to the third, 4x, none of those are like terms and they can't be combined. So therefore, at this point, this is in what we call simplest form. And we look at the highest power. The degree is 3. Why is the degree 3? Highest exponent is a 3. Now, the importance of that is x to the third for most values. X to the third is the biggest function, or I should say maybe the largest moving function of all of these values, right? So like, for example, if x is 3, then this value will be 27. You'll have 4 minus 9, 27 minus 12. So this will have the highest value. Um, it produces the biggest like domination of the graph. And so the way that the graph is shaped, its function, its twists, its turns, are mostly dependent on x to the third. And that's the same thing that happened, if you recall, if you think about it, the same thing happened with parabolas, right? So let's say you had the function x squared. So you had, f of x equals x squared. And the graph of that is a parabola. But no matter what you added to x squared, whether it was, say, x squared plus 3x minus 4, or whether it was x squared minus 10x plus 1, or whatever the function was, right? They all formed parabola graphs. Toss a negative, maybe it opened upside down. But they were all graphs of the parabola, and that's because x squared is a parabola shape. Even though the 10x, 1 linear, and they're large numbers, x squared is always going to dominate the conversation. And so all these graphs all look the same. Different places on the graph, different stretching, narrow, skinny, up, down. But at the end of the day, they all have a similar shape because x squared dominates how that graph looks. The same thing happens for all powers. So x to the third graphs will all look pretty similar. If you recall, we looked at an x to the third graph a bit during lesson 1 when we looked at the function that you get when you make a box. So if you remember what that function looks like, most x to the third functions will look pretty similar. When you look at d, the same thing here. You have an x squared, you have another x squared, you have an x, but that x to the third term is going to define, really it's going to be the one that defines what the function does. So that's why the degree is important. Knowing that both a and d are degree 3 is going to say that they look somewhat similar, despite what the other numbers are doing. B is a degree 4, and all x to the fourth functions will have a particular look as well. X squared, as we said before, degree 2, and they're going to look like parabolas. What we might wonder is what the effect of, say, an x to the 1/3 is going to do. Wonder. Okay, so degree is super important. Now, then again, the question then is, what is a polynomial? An expression of more than two algebraic terms, the sum of several terms that contain different powers of the same variables. But there's one big key here about this that's important, is that the powers must be positive um, whole numbers. So for example, when we look back here, okay, sorry about that, a little bit of microphone trouble there. Okay, let's take a look. So we were wondering what exactly is a polynomial. So A is a polynomial because it has four terms. It has a 4, it has a minus x squared, a positive x to the third, and a minus 4x. And when you have those together, we have four separate terms. All the exponents of the variable have whole powers. Therefore, we have a polynomial. B is also a polynomial. D is also a polynomial. But C is not. And the presence of the 1/3 is a big deal. So what winds up happening is this makes the graph produce something unexpected. And we can take a look at the graph of that a bit later on, okay? As to why, that, it will look kind of like a parabola, but this has a funkiness to it that we don't really, it produces some exceptions in the graph that we don't like to deal with? Okay. A, so we've also talked about this one during lesson one as well. A relative maximum point um, forms like a little peak in the graph. So, changes from increasing to decreasing, right? Um, and a relative minimum function changes direction from decreasing to increasing. So making the point a bottom in the graph. And, it may not be the absolute highest or lowest point, but when you look at the graph, it's pretty clear that it's higher or lower than the points that are around it. We'll take a look at a few examples of that. Okay, so here's some examples of some polynomials, right? So 3x squared. 3x squared is a polynomial. It's one term, just 3x squared. And so we call that a monomial, is another word that we can use. Binomials have two terms. So keep in mind what a term is. A term is some expression with numbers and variables um, combined under the operation of multiplication or division. Um, as soon as you start adding in addition and subtraction, that separates the terms from one another. So 5x is a term, 8 is a term, and so therefore we have two terms, and now we call that a binomial. 4x squared minus 9x minus 10, that's a trinomial. And we've talked about trinomials recently as well. But all together, they form polynomials. Monomial, binomial, trinomial are just special cases of 1, 2, and 3 terms. Once you get to 4 terms, 5 terms, 6 terms, we just call them all polynomials. Okay, so degree, right? Um, if there's no power of x in a polynomial, then it's called a constant, right? So like the number negative 24. Some of the other examples had just a number of 2 or 4. 0 degree, no x's, no powers of x, therefore we call that constant. Functions like 2x minus 8, first degree, because you can picture this as 2x to the first minus 8, same idea. X to the first power, that's linear. So all linear functions will form a line, pretty similar characteristics. Second degree, they have an x squared as the highest exponent. They're quadratics. Third degrees are called cubics. And again, lesson one, we looked at a box and it had a cubic function in it. And it had a x to the third power. There are other ones like x to the fourth is called a quartic and x to the fifth is called a quintic, but we usually don't talk about those as much. Once you get to cubic, it's usually about the best that we need for most uses. Okay, now let's talk graphs, right? And even though you don't know much about what x to the third graphs might look like or x to the fourth graphs, we know enough that we could certainly match up graphs. You'd be surprised what you can do. Okay, let's see. Let's start. We're going to match up. We have 6 graphs and we have 6 equations. Okay, let's match them up. So, for example, any of these that we know, equation C, y equals negative 15. Well, that's just a number, right? There's no x. Because there's no x, um, the most important thing here is that it has no slope. Or the slope really is 0. It doesn't rise, doesn't shrink. There's no, for the run, there's no rise up and down. So it looks like that's going to match graph A because it's just going to be a horizontal line at negative 15. And we have that. Okay. Let's match up some of the other ones. What about 4x minus 15? Now, this is linear, x to the first. And we know it's linear because it has a degree of 1. And, that's graph C. And just to match, we have a negative 15 for a y-intercept. Certainly matches there. Okay, perfect. So let's match up some other ones. Negative x squared minus 5x plus 24. Well, negative x squared is going to be a parabola, degree 2, and opens down. That looks like that's going to be graph f. How do we know? Y-intercept of 24, y-intercept 24, perfect. Okay, so now let us look at a few other ones, right? Um, Equation f, there doesn't seem to be any other parabolas on here. These graphs look kind of funky. We know they're not parabolas, so we don't think equation f is going to be one of those. So guess what? No match. So let's go back up here. And now we have equations A and B. We have graph D, B, and E. Which is which? Okay. Now, at first, this is going to seem kind of hard, right? But let's think. Okay, first off, equation A. Equation A, oops, didn't mean to do that, has a y-intercept of negative 12. So even though it's got an x to the fourth, it's a degree 4. And though we may not know what it looks like, this is true for all polynomials. If you have that constant term of negative 12, that's going to be the x-intercept. Or sorry, y-intercept. How do we know? Because if you plug 0 in for x, no matter what the powers are, all that's going to be left is the minus 12. So is there a graph here that has a y-intercept of minus 12? D. So it turns out equation A matches graph D. All right. And oh, that's a funky looking graph. And so we're going to talk about it. But if you think about it here, degree of 4 actually is going to have 4 pieces, a down, and then an up, and then a down, and then an up. So it's got 4 pieces to it. That's kind of what degree helps to do. So let's look at equation B. Equation B, x to the third plus 2x squared plus 15x. What's the y-intercept? 0. Oh, but both of these graphs have a y-intercept of 0. What else then? Well, let's find out. Let's see what else this is. Okay, this seems to cross at negative 5. Okay, so negative 5 here, maybe roughly? I don't know. Let's give it a try. Can we maybe take equation B and maybe plug negative 5 in? Let's see what happens. You get negative 5 to the third power plus 2 times negative 5 squared minus 15 to negative 5. Okay, 5 to the third power is 125. Negative times negative times negative. So that's negative 125. 25 times 2 is 50. And negative 15 times negative 5 is positive 75. So negative 125 plus 125, hey, that's 0. Guess what? Looks like it's got an x-intercept. All right. So, sorry. Okay. So, it looks like equation B matches graph E. And that makes sense if you think about what happened above. It's an x to the third graph, so it's a degree 3 because it's got an up, a down, and an up. Now this one does too, but this one's got something kind of funky going on here. Kind of an odd little flat part to the graph that's not like a exact hump. Um, so that one has a little bit of a different behavior to that one. So looks like we don't know what the equation is, no match. Okay, perfect. All right. So we can Talk about a few of these. Using graphing technology to write equations for polynomial functions whose graphs are listed. Okay, let's take a look. A first degree polynomial function whose graph intercepts the vertical axis at 8. Well, vertical axis at 8, that means it's a y-intercept. So what would be a function for that? First degree, so it's got to be linear. X plus 8. Because that'll be linear, it'll be first degree, and we'll cross the axis at 8. Okay. A second degree polynomial whose graph only has positive y values. Okay, so the second degree, which means we need um, so that means we need one that's got a positive y value, so it never crosses the x-axis. Okay, so it's one of those, like, it's got to be a parabola, and the parabola is going to have to, like, if you were to solve it using the quadratic formula, it would have no solutions. So maybe something like if I did, say, uh, x squared plus 2x plus, say, 30. That's a good example of one right there. Um, so that would never cross the x-axis. Okay, a second degree polynomial function whose graph contains the point 0, -9. Oh, that's easy because, again, that's a y-intercept. So for number 3, I could just do, you know, 3. I could do x squared minus 9. A third degree polynomial function whose graph crosses the horizontal axis more than once. Ooh. Okay, maybe we better Desmos these. So let's take a look. Do we have that? Nope. Wrong one. Let's do some, pull up my other account. Let's do some Desmos. Graphing calculator. So let's take a look here. Let's say we did x to the third. It's going to look like that. So there's my basic x to the third graph, and it has to intercept the x-axis more than once. Oh, let's just do that. Okay, minus 2x. Now, mind you, I had no idea what these graphs will look like. Excuse me, I just played around with this. So x to the third minus 2x. Okay, that's an example of one. Your results may vary. Again, you're just looking for something that crosses the x-axis more than once. So if I scroll back here, so 4, x to the third plus 2x certainly worked here. A fourth degree or higher polynomial function whose graph never crosses the horizontal axis. Okay, so let's try that. X to the fourth. Okay, x to the fourth. We tried x to the fourth minus 2x. Ooh, what an odd-shaped graph. But now, how do we get the graph away from the x-axis? I don't know. Let's just add. Oops, that's not what I wanted. I don't know. Let's just maybe add. No, add 2 to it. Add 3 to it. Plus 3. There. There we go. There's an example of a fourth degree graph that never crosses the x-axis. And I can maybe spice it up a little bit. Let's do maybe x to the third. Ooh, there's a fun looking graph. Plus x squared. Maybe do 2x squared. No, 3. Maybe minus 2 x squared. Let's just do minus x squared. There we go. So x to the fourth minus 2x to the third minus x squared plus, but now we can't do 3 anymore. Maybe we'll change it to a 4. 5. There we go. So x to the fourth minus 2x to the third minus x squared plus 5. There's an example of one, and it's a fourth degree. Look, it's got 4 parts of the graph. 1, 2, 3, 4. Now, other ones didn't quite have look like they had four parts to it, and they were kind of shaped kind of funky. Um, More on that a bit later on, I suppose. Okay, so let's write that in x to the fourth. So it's going to look something like this. We had, oops, here's my graph. For 5, we had x to the fourth. What is it, minus 2x to the third, minus x squared plus 5. And that one does not cross the x-axis. Okay, perfect. All right. All right, and here's some features. Again, we'll just, we can save this practice for a little bit more in class. Um, but we can look at, another question we come up with is like relative minimums and relative maximums. Um, so in this particular case here, we have, relative max. How do we know that that's a relative max? Because it's like a hump of the graph. It's a little bit higher than the points around it. Okay. And it looks like maybe that's around -3, maybe a little bit higher than -3, like maybe -3.1. Here's one maybe around -1. This is a min. It's got a little valley. Sometimes we call it the valley of the graph. Around -1. And maybe around 1. Here's a max. And here's a min. Looks like maybe around 4.5. So min at 4.5. Okay. So here's a kind of a graph, and this is a fifth degree polynomial. It's got one, two, three, four, 5 pieces to it. So fifth, the degree of the polynomial can tell you potentially how many different ups and downs you can have on the graph. The more degrees, the more ups and downs the graph can have. And that's kind of a big thing there, okay? Um, so that's a little bit about the properties of polynomials. Um, and So in the future, we're going to work on just what happens when you try to combine polynomials and go a little bit further into understanding the behavior of these maxes and mins and the ups and downs. Okay? All right. Well, I will leave it here, and I hope you have a great night.